Good morning, everyone. I'm Charlie Jordan, and once again this week I'm bringing you a lesson for Algebra II with Trig. This week, once again, we're going to focus on essential concept number 1, which is focusing on the graphs of exponential and logarithmic functions. If you tuned in last week, you saw where we focused solely on exponential functions, and I told you this week that we were going to learn about logarithmic, and that is exactly what we're going to do. So before we can even start worrying about the graph of a logarithmic function, we need to answer this question: what is a logarithmic function? So up here I have displayed two graphs. The first one is a red graph, and it is the equation y equals 10 to the x. Now the x is in the exponent, so we know from last week that that is an exponential function. The blue is y equals log x, so logarithmic function. This is the question I have for you. What do you notice about these two functions? They're inverses, right? We learned about that probably back in January, depending on when your teacher got to it, but it was probably around January, close to the beginning of third quarter. We learned that two functions are inverses if they reflect across the line y equals x. And I have y equals x graphed up here on this graph, and so you can see indeed that if we were to have this on a piece of paper and we were to fold our paper along this line, that they would be these two functions would be directly on top of one another. So they are inverses. So our standard form of a logarithmic function is y equals log base b of x. So this is something totally different. The only time you've ever seen log prior to this may have only been on your calculator. So let's break it down and say, what does this mean? We have this little b. It's written as a subscript, right? That's our base. Every time we'll read this as log base b, okay? Now, whatever is next to our log is what we're taking the log of, log base b of x. And finally, we have y equals, and we know that the y is going to be our answer. The important thing I want you to know, though, is base is written as a subscript, and then what we're actually taking the log of. But still, what does this mean? I told you how to read it, but what does it mean? So the question here is, first, our base is 5, right? But we're taking the log of 25. But how does all of that work together? So what this is asking is, what can I raise 5 to in order to produce 25? So what does the power of 5 need to be where it will equal 25? 2, right? 5 squared is 25. So that's what is happening with a log. What do I need to raise the base to in order to equal what I'm taking the log of? So there was our question. What can we raise 5 to where it equals 25? Now, how can we evaluate logarithmic functions? Those numbers were simple. What if they're numbers that we're not really familiar at working with? Maybe they're numbers that are harder. Maybe they're an irrational number, right? Okay, we can convert them to an exponential function. And we are very comfortable with exponential functions. We're very comfortable with raising numbers to other powers. We've been doing it for quite some time now, right? Probably all the way back in middle school may have been the first time that you heard the term squared, 2 squared. So we've been working with exponents for a while. So we're going to relate it to something we already know. So we have y equals log base b of x. But how do we convert this? How many of us can listen to a song on the radio, and by the time that that song goes off, we already know the chorus? By the second or third time, we pretty much know the entire song, right? Okay, so I'm going to teach you this saying to maybe help you learn how to convert. Maybe your teacher's already taught you and it's just not quite getting there. So let's look at this. It says the base to the power equals whatever you're taking the log of. The base to the power equals whatever you're taking the log of. One more time. The base to the power equals whatever you're taking the log of. But what does that mean? What is our base? B, right? Okay. Now, last week we discussed how the number that's being raised to a power in exponential can also be referred to as our base. Our growth factor can also be referred to as our base, because guess why? This b is going to turn into the base of our exponential function. So the base to the power equals whatever you're taking the log of. What are we taking the log of? X, right? So we need to equal x. But we know that we have to have something in the exponent. But what is that? What goes in the exponent? The answer to the log problem is the exponent. What is the answer to our log problem? Y, right? Y is our answer. So we have the base to the power equals whatever you're taking the log of. The answer to the log problem is the exponent. But maybe that's still not quite clicking with you. Let's look at it a little bit more. We have these two equations still up here, and I want you to just look at them with no other fluff on the screen. Look at them and see what can you notice about these two equations. Maybe you notice that the x and y swapped places, okay? The x was originally right next to the b, but now the y is right next to the b. Maybe that was something you noticed. Maybe you noticed that log equals y, but the exponential equals x, meaning that the y was alone, but now the x is alone. Those are just two. You may have came up with so many different ones, but those are the two that I could predict that you have possibly came up with. I want you to look at these three examples. Now with actually numbers in them, I want you to look at the three and see if you notice any patterns here. Maybe you noticed that our bases are still our bases. We talked about that before, but maybe you can see it a little bit more now. Our base of 5 in our log problem is our base of 5 in our exponential problem. Our base of 16 in our log problem is the base of our exponential function, right? Maybe you notice that what we were taking the log of was originally on the left of the equal sign, and now in our new problem it's on the right. See how 4 is on the left and then 4 is on the right? Maybe you notice that 2 was originally on the right, but now it's on the left. And x was originally on the right, but now it's on the left. Maybe you notice that 5 and 25 were stuck together, but now 5 and 2 were paired together. Maybe you notice 16 and 4 were originally paired together, written next to each other in the equation, and now you notice that 16 and x are written next to each other. There are so many different observations that you could have made, but the important thing is that you are finding a pattern to help this converting stick. Now, what else I'm going to show you is something that has proven successful. One of my students did this a few semesters ago, and she draws this circle thing. I don't really exactly, it looks like a circle when she draws it on her paper, and I tried to recreate it as best as possible here on the screen because maybe that'll click with you. She's had great success carrying that over and tutoring her peers with this same method, so maybe it'll work. She writes everything vertically, right? Okay, most of us do. So she draws, when she converts, she draws her arrows on her paper. She draws her base, and she draws an arrow down and she rewrites her base. Then she takes whatever her log equals, the answer to her log problem, and she draws her arrow around and writes it next to her base. Okay? Lastly, then she takes what she's taken the log of, she draws her arrow and she brings it this side. Maybe one of these ways have helped converting click just a little bit more, because converting is so important. All right, we know that exponential and logs are inverses, which is what allows us to go back and forth between the functions. But it's so important to convert. But why is it important? Because here in the next weeks, we're going to switch and start solving logarithmic expressions and equations, and converting is going to be important. Today, though, we're going to be graphing logarithmic functions, and we're going to see how converting will help make our process so much easier depending on what kind of numbers we're working with. So, without further ado, let's begin graphing. Our function is log base 2 of x. So, we discussed that this base means that I need to raise the base 2 to some number to equal x, right? I want you to think about this. In the past, we have worked with square root functions, right? And when we graphed square root functions, we had to specifically and purposefully and strategically choose our x, right? So when we worked with square root functions, oftentimes we would choose numbers that were perfect squared. We would choose 1, 4, 9, because we knew that we could take the square root of those numbers and get a nice, pretty number. What we didn't do was we didn't take the square root of 2 because that would produce an irrational answer, right? We're going to use the same idea here. So what numbers can we raise to 2? Any number, right? But do we want to raise 2 to 25? No, that's going to be very large, right? But we could raise 2 to 0, 1, 2, 3, and that's going to produce us a variety of answers, right? Well, that's going to help guide us with what x's we choose. So the first x we're going to choose is going to be 1. So our question is, what can we raise to 2 in order to produce 1? 0, right? What can we raise to 2 in order to equal 2? We can raise it to 1, right? What can we raise to 2 in order to equal 4? We can say 2 squared, right? And lastly, what can we raise to 2 in order to equal 8? 3. Now, I left this one spot blank, right? Okay? Now, here we have 1, 2, 4, 8. What number could go right there in that spot that maybe I left blank on purpose? Maybe 0, okay? Is there any number that we can raise to 2 in order to equal 0? No. Remember, we talked about this last week, okay? It's going to be undefined because there is no number that we can raise to 2 in order to equal a 0 or a negative for exponential functions, right? We had a whole discussion about that. That's going to carry over here as well. So it's undefined, but what does that mean? That means we have a vertical asymptote at x equals 0. So let's graph this. Remember, we're going to plot all of our points. And once again, I have 1, 0 labeled. Why? It's our x-intercept, right? And those are the kind of things that we're trying to pick out when we develop the graph of a logarithmic function. So now we know that we're going to have an x-intercept at 1. I'm going to connect it with a nice smooth curve, but what did I leave off? What else is super important about this graph? The asymptote, exactly. So now we have an asymptote at x equals 0. On your paper at home, make sure you label that nice and pretty. X equals 0. I have it here. I should have moved it over. What happens though? So already with this, it could possibly be confusing because you're having to think backwards, and you may have never thought backwards like that before, other than in square roots and cube roots and different things like that. But maybe you haven't done it too often. So maybe this is still kind of confusing. But what happens if we have a base that's even more difficult than 2? What if we have a base of 15, right? Okay, so what happens if we have the function y equals a natural log of x? What is the base whenever we have a natural log? The base is e, and once again, what is e? E is an irrational number like pi, right? So pi is 3 point all those numbers, okay? E is 2 point all of those numbers, all right? It is something that we would not be able to come up with solid whole numbers to work with like we did in the previous example. So what are we going to do? We're going to convert, exactly. That's the whole reason when we spent all that time converting. So we have the base of e. Okay, it's still our base of our exponent. We were taking the log of x, so now it equals x, and then the y is going to be our power because it was the answer to the log problem. So maybe you were able to use one of the patterns that you noticed earlier to help you convert this. Now, but what do we know about inverses? We converted, but we want to finish finding the inverse, so how do we do that? We swap x and y. Very good. So now we have y equals e to the x. So this is our inverse function, and this is what we want to graph. Well, this is what we want to use to graph. There we go. So we're going to use the same type of table that we used last week when we graphed exponential functions, going from -2 to 2. Now, we remember, let's go back and recall, we had to replace the x, our exponent, with these values. So we're raising it to the -2 power, e to the -2, then to the -1, and so on. So we did all of this last week. We learned how to do this. So I already did the calculations for you. Now, one thing I want you to notice, e is an irrational base. I have 4 of our outputs written to the 100th place. Not the 100th, just kidding. I have it written to the 1000th place. I have it written to the 1000th place. So do you think that my calculator generated only 0.135 whenever I plugged in e to the -2? No, it produced an irrational number, right? But I rounded to the 1000th place because I wanted to be as accurate as possible. So that's why I rounded all those. Now, why is e to the 0 not an irrational answer? Because we know that any number, no matter what number it is, raised to the 0 power always produces 1. Very good. Remember, we talked about that last week too, but you already knew that from Algebra 1. So now we have our all of our values for e to the x. But e to the x is the inverse function. And we don't really want to graph e to the x. We want to graph y equals ln of x. So what are we going to do? What is the special relationship whenever between two functions that are inverses of one another? You're exactly right. The x's and y's are swapped. So we need to swap the x and y. So instead of our ordered pair being -2, 0.135, now our ordered pair is 0.135, -2. We're going to do the same thing for the remaining 4 coordinates. So here they are. We want to graph these coordinates. Once again, I have 1 point labeled and only 1 point. It's 1, 0. Why did I label that point? It is our x-intercept, right? One other thing I want you to notice is look at these values. See how whenever we're getting closer to the x-axis, how these values are getting close and close and close and close. I said x-axis. So we're getting closer to the y-axis. We're getting closer and closer and closer to the y-axis, but are we touching the y-axis? No. Are we crossing the y-axis? No, because once again, we have an asymptote at x equals 0. So hopefully you can see this green line that's drawn on your screen, and that asymptote is x equals 0. So since we converted to an exponential function, we were able to use the inverse to help us arrive at the actual function y equals ln of x. So let's look for some patterns in both of these functions. Since we've already graphed 2 log functions, let's look at them and see about some things that we can gather. So we're looking here and we notice that both have the same intercept, right? Both have the same asymptote. They have the same shape going on, but what do you notice about the difference in the shape of our log base 2 and our log base e, our natural log? This one gets a little bit taller, huh? Okay, so the base here is 2, and the base for natural log is e, which is 2 point all of those numbers, so which one's larger? Natural log has a larger base, right? But which function's taller? Exactly, our smaller base. So the larger your base is going to be, the closer to the x-axis you are going to be. So just keep that in mind whenever you're graphing. Let's compare exponential versus logarithmic functions. Exponential functions, we know that the horizontal asymptote is y equals 0, that it has a y-intercept at 1, that the domain is all real numbers because we could plug in any number of x, right? Last week we talked about plugging in all the way down to -infinity. okay? And that our range was only going to be greater than 0 because we were not going to have any values that were at 0, because that's where asymptote was at, and we weren't going to have any values below 0, were we? But what can we gather about logarithmic functions? We've already talked about it. We have a vertical asymptote at x equals 0. We have a x-intercept at 1. We have, instead of our domain being all real numbers, now our range is all real numbers, because we know that inverse functions, everything's going to swap. And our domain is now x is greater than 0. Hopefully, by just knowing the definition of inverse and understanding that concept, which you developed just a few months ago, that you would have already been able to come to these conclusions without graphing it. But we verify these conclusions, by graphing it. And then we see our graphs. So an exponential function is going to shoot up very quickly, and a logarithmic function is going to grow more slowly. But why do logs matter to you? We use them in acoustics, we use them in astronomy, we use them in chemistry. Guess what else we use them in? Engineering. How many of you out there want to be engineers one day? You're going to use logarithmic functions. We also use it in I can't even say the word right now. I'm not going to try to say it because I'm tongue-tied. The study of earthquakes is what we use it in as well. And we use logarithmics anytime we're trying to notate a situation where the data points vary greatly. Okay? But still, what does all that mean? Maybe none of these are your interested career fields. Okay? How many of you have it on your bucket list that you want to go skydiving? Not me, but maybe you do. Maybe your career path is the military and you are like, I'm going to jump out of an airplane. Okay, maybe that's your goal. So skydiving, the skydivers have a tool that allows them to know what height they're at. But that tool uses logs, and it uses the pressure, right? So the tool's measuring the pressure based on where the skydiver is located, and it's converting that into the height so the skydiver knows exactly when to release his parachute. So here is the graph of this function, okay? This is 40,000, and it's in meters, height is in meters. Pressure is measured in pascals. Units are important, even when we're not in science. So let's talk about some things. I zoomed in this graph much more closely because here are some facts. Whenever you go skydiving, you're going to jump from roughly 13,000 feet, maybe a little bit less depending on the weather, which is about 4,000 meters. Once you jump, the parachute needs to be released at approximately 760 meters. It's really bad if your parachute's released at the wrong time, right? Okay, maybe it messes up your landing zone. Maybe you're released too high and you're getting so cold, right? And there's the pressure up high is so much lower than the pressure, closer to the ground. So there's all these things that could go wrong if you release your parachute too high. Maybe not like life or death situations, but what happens if you release your parachute too low? Then it really could be life or death, right? So we need to make sure that our parachute's releasing at just the right time, and a log guarantees that that happens. So if we're jumping at 4,000 feet and we're 4,000 meters and we're releasing at 760 meters, this is the portion of the graph that we're actually worried about. Now, we don't know how to solve one of these functions yet. We will, but we don't know yet. But we can use a graph to find out when exactly your skydiving instructor, like what pressure does his tool need to read to know when to release the parachute, right? When is it going to tell him that the height is 760 meters? So here we're at 5,000, so 760 is before even our first grid mark. And we're going to trace that over. This grid mark is 90,000, and 760 is somewhere in between 90,000 and 95,000. We're guessing it's a little bit on this side of 93,000, maybe 91,000, 92,000, but we can use graphing tools to help us find exactly what the height is. What the pressure is, because we know the height's 760. So now we can see that at 760, the pressure is 92,240 and some decimals of pascals, right? So that's when our parachute needs to be released. So this graph has now been reflected across the x-axis, but why? We had a negative, right? We haven't had a negative before. So, like I said earlier, we don't know how to solve this problem algebraically yet, but we're going to. So tune back in next week and stay home and stay safe.